So I was telling you a whole story about Levi-Tristram signatures for knots. I told you that they're not invariant. Livio told me that actually what I proved is that Levi-Tristram signatures are not just not invariants, but they are concordance invariants almost everywhere. And we talked about the proof of Litherland's theorem about linear independence of torus knots, and we had this nice formula for Levi-Tristram signatures of torus knots that you will all have proved yesterday after the example session, because it was one of the exercises. Right, and so the plan was what, how, and why. So maybe today I want to motivate a bit why I like thinking about these questions and why I think people might care about these questions. And maybe along the way clarify some things that were said perhaps not so clearly at the end of Tuesday's lecture. So remember that we talked about links of singularities. We said that if I have a function, maybe a polynomial, into variable that is irreducible as a power series, then this gives me a knot in S3 of small radius, technically, but let's ignore this, which is given by intersecting V of f, so the zero set of f, with a small sphere centered at the origin. And in a way, this is what the theorem that I stated on Tuesday, Browner's theorem, told you what these knots look like. And in a sense, what we were doing is we were studying a static problem. We're looking at one polynomial, and we're looking at what happens to this polynomial when we don't move anything. So you might wonder, well, what happens if you start moving your polynomial around a bit? What happens in one parameter families of such objects? So this is the study of the theory of deformations. So a deformation of a singularity f0, 0. So I have one polynomial f0, and I have the origin in C2, is a one-parameter family f from a small disk in C containing the origin times C2 to C, which I think of as a polynomial family or a power series family. It doesn't really matter, such that f of 0 x y. So I'm going to put coordinates t here and x and y here. This is small f0 of xy. And just for convenience, I'm going to call the function that sends xy to ft xy. This I'm going to call ft. So I have three variables, but I'm really thinking about the t variable as being a time variable, and I'm looking at what happens when I change the t parameter. So, examples. You can basically write down whatever you want, but I can think of looking at this specific one-parameter family. I want to look at of f t x y to be xp plus yq, our good old friend. plus t of xa plus yb, and I want that, let's say, p less than q, a less than p, b less than q, and ab and pq coprime. This is a perfectly good, yes, please.
So here, I assume we want all of our f's and t's to be polynomials?
Yes. I'm thinking of, maybe I'm thinking about a polynomial in 3 variables.
Okay.
And I kind of want that the polynomial stays locally reducible as a power series, but that's not so important. I want to avoid having multiple fibers, but yeah, let's sweep these things and do work. So what does this guy look like? This guy, if we look at f0, and f0 is just xp plus yq, and this is something we know and understand very well. And ft, for t non-zero, actually you can secretly change variables. Let's look at f1 of xy, just to be very concrete. This is xa plus xp plus yb plus yq. And you can find a change of variables which is actually separate in x and y. That tells you that this is the same thing as maybe something that we'll call f1 tilde of x tilde y tilde, which is just x tilde to the a plus y tilde to the b. Essentially, you can take the 8th root of this polynomial. This is well defined as a power series. And the bth root of this polynomial, this is well defined as a power series. And you can do a power series change of variable that transforms your f1 into this function. And what happens in terms of links, if we think about links of singularities, we have that this function, the f0 is associated to the torus knot tpq, and this is associated to the torus knot tab. And in a way, we've crucially used that a is smaller than p to make this change of variable, and that b is smaller than q. And the mantra that maybe one should keep in mind is that deformations make links of singularities smaller. If a and b are smaller than p and q, then the torus knot tab is in many different ways, in many different, by many different standards, is smaller than tpq. And the question, so this is actually something that we will make precise in a second, but the question is, given two links of singularities, let's say k1 and k0, when does there exist a deformation from f0, well, a deformation ft, such that the link k f00 is k0, and the link of k f epsilon at 0 is k1. So if I have a deformation, if I have two algebraic knots, so two torus knots that are one smaller than the other in some sense, can I find a deformation that realizes this relation of being smaller than? And so far, I think that there are no surfaces in the picture and no 4 manifolds in the picture. So let's try and make some surfaces and some 4 manifolds appear and connect back to what we were doing earlier. So the key proposition is that if there is a deformation, so I'm going to shorten this and say that in this case there is deformation from K0 to K1. And just keep in mind that, I mean, I'm going to try and stick to more or less the terminology and the setup throughout the lecture, that this is the larger knot and this is the smaller knot. And if you want to view things in this picture, I have my delta, my two disks here, I have my origin, I have the singularity of F0, so this is F0 is equal to 0. And I have then F1 equal to 0, or F epsilon equal to 0. And the central singularity, the singularity of F0, is the large one. So in some sense, the special one. And this is the small one. Okay, let me make sense of what larger and smaller means via this proposition. So if there is a deformation from K0 to K1, then there is a cobordism sigma from K1 to K0 of genus G of K0 minus G of K1, where G is either the cipher genus or the slice genus. You can choose whichever you want. For algebraic knots, it's the same. Yes?
Why is this not like a symmetric thing? If there's a deformation from K0 to K1, why is that not just the one from K1 to K0?
Why?
Where the T is in the polynomial. If you set T to 0 in this property,
Yeah, so maybe think about it in this way. Actually, the simplest example that you might want to have in mind is looking at the one variable case. What is a singularity in complex dimension 1 is having multiple roots. If you have a polynomial with multiple roots and you deform it, around it you will have polynomials with smaller multiplicities. Let's say you have a polynomial of degree 2 with 1 double 0. When you give it a bit of a kick, the polynomial will develop multiple roots instead of simple roots instead of having one multiple roots. But if you have a polynomial that has simple roots and you give it a bit of a kick, it will stay a polynomial with simple roots. You will not create singularities from non-singularities by giving small kicks. If you want to create some topology in the link, you need to squash some topology from somewhere. And this is essentially what this picture, what this proposition tells you. There is a direction in this context. And if you want, if you're familiar with symplectic contact topology, there is a contact symplectic explanation. There's one convex side and one concave side, and you have a cobordism that has a direction from one to the other. It's something that...
say, just trying to fit this with my kind of geometric understanding. In like the picture you draw those of like in green curves, could you not also define a deformation centered at the green curve, where the disk is just like a smaller disk that's centered at the green curve, but then still includes which then gives you a deformation on the green curve?
There's a key word here. The keyword is small.
Okay.
So if I have such a family, then I can find a small disk which in my picture also includes this green point, so maybe I will draw the picture to include this point, such that every fiber in this disk that is not the origin look like any other fiber.
Okay, that's how we're meant to be tracking single pair.
Yeah. Whereas if I take this point and I take the same disk, but I think about it as being centered here, this disk is not small because I'm doing a lot of work to create some singularities. But yeah, that's an excellent question.
Great, that makes sense.
Yeah.
Could this difference between a large and small not have some relation with the organization of the cobordism?
Which cobordism?
Well, given from by the proposition.
Aha. Yes. No. Not as far as I can tell. No.
So maybe you can see the proposition again. In this composition, G is the minimum cipher genus.
G is the cipher genus. This is a knot invariant, not a surface invariant. This is the cipher genus.
Doesn't seem so obvious. Will you prove it?
Yes. Yes, that's the plan. Yes.
Sorry, just before we get there, is there a preferred direction of this cobordism?
Yes.
Written from K1 to K0.
Yes, there is a preferred cobordism. That is the symplectic direction, if you want, or the complex direction in some sense. Yes. And I did write g of k0 minus g of k1 and not absolute value. That is not by accident. In particular, if g of k1 is larger than g of k0, there can be no such cobordism. So, yeah, I'm sorry, I'm going to draw the same picture, basically, but whatever. So I have my one parameter family. Of knots, of curves, and I see v of f0 here. And since I see v of f0, by definition of link of singularities, I can find a small ball centered around the origin that witnesses the fact that k0 is the link of the singularity of f0. There's a small neighborhood of the origin in C2 where the manifold V0 is a cone over K0. Good. Now, I give F0 a bit of a kick, and I go to F epsilon for some certain epsilon. And when I go to F epsilon, so this is V of F epsilon, what do I see? Well, I see V of F epsilon, and there is a small ball centered around this point here. That witnesses the fact that the link of F epsilon at its singularity is K1.
So the picture is kind of wrong, though, because the cusp is at the same point.
The cusp can be at the same point. I didn't technically say that I'm looking at the singularity at the origin, but yes, technically you're right. Technically you're right. Technically I should draw a second picture, but I want to emphasize that there's some movement in time that is going on. So technically Gregor is right. Technically these 2 points are the same point, but this picture still allows me to make the point that I want to make. So here I see K1 appearing. And since I've given only a small kick to my V of F0, and I knew that there was no singularity here, this is a small neighborhood already. It's big, but it's small. When I move in time from t equals 0 to t equal epsilon, I keep having a transverse intersection with the boundary. And if I have a transverse intersection with the boundary at all points, the knot moves around, but it stays the same knot. have an isotopy of transverse intersections, and the intersection stays transverse and just is being moved around with an isotopy. So what I see here is not K1, it's not the link of the singularity of f epsilon at 0, but it's still K0. I haven't moved the link K0. And now what do I have? I have V of f epsilon. I have removed a small ball centered around its singularity. And I have whatever is left. So the difference is a non-singular, actually, let me, surface that interpolates between F0 and between K1 and K0. And to answer Evan's question and maybe partially Lorenzo's question, in here I have, well, on everything I have a symplectic form, and I have that this sphere that I have removed is the concave boundary of the symplectic form manifold, which is the difference between the two, and in here I have the convex boundary. So from the symplectic perspective, there's a positive end, and a negative end. So where does this surface live? This surface lives in the difference between two balls, one nested inside the other. So this is just S3 times the interval. Yes, Gregor?
Only one feels cheated there?
Yes, you should be.
I mean, it works in real life. The red thing also intersects the green circle.
But you don't care.
And so I could run the same argument and say that I see something from K0 to K1.
Why? No, if you look at the red surface.
I see something from K1 to K1 again?
Yeah, and that's just a product. You're absolutely right. You see something from K1 to K1, which is the product.
So, sorry. The green. I know that's K0. I mean, if I take any sufficiently small disk around the red cast, I'm going to see K0.
Yeah. Oh, so you see something. Sorry, you see something from K0 to K0, which is just a trivial concordance. It's just an annulus, because you have the Cohen theorem that tells you.
No, you're telling me if I intersect the green disk with the green.
Yeah, but the green disk is not the same thing.
I see K1.
Yeah, because the green thing is not the red thing.
But I mean, they are concentric in real life.
Yeah, but the balls might even be concentric, but you're intersecting different things. You're moving your surface.
Anyway, never mind, please go on.
Yeah. So there's one other point where you should feel cheated, which is the fact that nobody tells you that Ft doesn't develop any more singularities. So I'm cheating a bit, and it's actually maybe perhaps not f epsilon that is non-singular away from that point, but I can further modify my surface to remove the singularities. So I'm sweeping some details under the rug, but not so much. So this actually needs a bit of extra work.
Is it like actual extra work, or because I somehow feel that the assumption of the small disk should say you that like if you vary small enough it shouldn't develop a huge.
I don't think that's true.
Okay. Because you have two parameters to control.
Yeah. I mean, you can think about two singularities that merge together into a more complicated singularity. Yeah.
I'm sorry. Can I just say what I understand from this?
Yes, please.
So when you're moving this in time, you're changing a singularity close by, but at a further distance away, it still remains transversal, and so the knot remains the same, and you get a convertism between the two knots.
Correct.
Okay. And since you're having two spheres, the convertism is S3.
Correct. So the only thing that's missing from the statement is the genus computation. So what about the genus? how do we compute the genus? Well, what I can do is I can do a further deformation and make Gregor really unhappy to draw it in the same picture. Well, no, maybe I won't. Maybe I will make Gregor a bit happier and draw 3 pictures now. So this is f0 equals 0. This is f epsilon equals 0. And now I do one further deformation in blue, where I do a completely random small perturbation that removes the singularity away. If I have any function, I can add something and make the function not have any singularities. Singularities are not generic. I can always give something a kick to remove the singularities. And the idea is that here I see v of f0, great, and k0 on the boundary. Here I see k1 on the boundary. And here I see a small kick of a small kick, actually a small kick of a small kick, and a small kick of a small kick is again a small kick. So what I see here is a deformation of this singularity globally. And I told you that the deformation of a singularity, if I look at the 0 set of f tilde epsilon, the 0 set of a kick is called the Milnor fiber that we talked about last time. This is something that fibers the complement of this curve. Well, is one of the fibers of the fibration of the complement of this curve. And I told you last time that the genus of this surface, this is a surface with one boundary component. It's a slice surface for k0. The genus of this surface is half the Milnor number. I don't know if I defined this, but this is half the Milnor number. And I said out loud that this is exactly the slice genus of the link, and that this is exactly the genus of the link, which I guess that Jeff will mention tomorrow at some point, perhaps. This equality is hard. This was proved by Kronheimer and Mrówka, but this equality is somewhat not too hard. And in here, I see also a kick, a small deformation of this singularity. So in here, I see the Milnor fiber of the smaller singularity. So in here, I see a surface whose genus is equal to 1/2 the Milnor number of f epsilon, which is the genus of k1. And the surface that I see in here, the difference between these two surfaces, so this bit here, is actually the same as this bit here, because the surface was already smooth, well, it was already non-singular around here, and when I give a small kick to a non-singular surface, I still obtain a non-singular surface, which is actually isotopic to the previous one. So all in all, I obtain a surface, a cobordism from k1 to k0, which has genus, which is the difference of the two genera.
So we're using it for these guys, the slice genus, cipher genus.
Actually, I'm not using this. I'm not using it because I'm just saying that the Milnor fiber has that genus. The fact that the fiber, the genus of the Milnor fiber is the genus of, is a cipher genus, is classic. It's a classical theorem. It doesn't use gauge theory.
The fact that the Milnor fiber, the genus of, sorry,
The genus of the Milnor fiber This was known to Milnor. And the part of the Milnor conjecture is showing exactly that the Milnor fiber genus is genus minimizing. So let's assume that you haven't gotten completely lost in this explanation, which is a lot to ask for. But even if you got lost, what's the bottom line? The bottom line is that cobordisms between algebraic knots appear naturally in the context of singularities of deformations of complex curve singularities. And the side note is that singularity theorists do care about these things. So this is maybe a bit to justify a posteriori that one might want to think about these objects, and one might want to say, well, when do such cobordism exists? When are they genus minimizing? What is happening in all of this context? Let's study cobordisms between algebraic knots beyond Litherland's theorem that tells you that there are no concordances. This is not the end of the story somehow. For me, it's more like the beginning of the story. Instead of just looking for concordances, which are genus zero cobordisms, let's look at actually quantitatively give bounds for the cobordism distance between two algebraic knots. And this is what I'll do for the rest of today. I did start at 3, right? Ish.
Is the converse true that if you have a higher genus, then you can always find a cobordism?
Thank you. So what restrictions on the existence? Short answer is no, this is not enough, and there's an easy algebra geometric invariant that tells you that you cannot have a deformation from certain guys to certain other guys, which is the multiplicity. I will not define it because I don't have too much time, but let's say a theorem or proposition. If there is a deformation from T PQ to TAB, and I always have this convention that P is less than Q and A is less than B. Jeff, you were wrong. Jeff left. Jeff was wrong this morning. He wrote T32. No, that's T23. Then A is less than B. So one measure of what it means to be larger for two knots, for two algebraic knots, is their Milnor number or their cipher genus or whatever. Another measure is the multiplicity, which you can think of, well, which actually agrees with the Braid index for algebraic knots, not just for torus knots. Sorry, I mean A is less than P. Thank you. Yes. So in particular, you cannot have a deformation from T to 37 to T34, even if the genus is much larger for T237.
So, for example.
Oh, no. Thank you. If you take that deformation up there and you just take Tx to the A, no, Ty to the B, and you just forget the x to the A term, then you get a deformation to something between, so TPQ to TPQ prime whenever Q prime is smaller than Q. But it's far from being true that B has to be less than Q. And actually, maybe I want to give one example, well, a family of examples perhaps. So let me say that this can also be proven purely topologically. The quickest proof is by far using algebraic geometry. The multiplicity is non-decreasing along deformations, and if you think about what it means, what the multiplicity is, it's basically a one-liner. So maybe a sub-question is, when is there a deformation from T, P, P plus 1 to T to N plus 1. And this is not, it appears, it really looks like a random question. It's not. This is related to the so-called AN realization problem in algebraic geometry, which is something that I care about, but not only me. And in a sense, you're looking at two very simple families of torus knots that are somewhat extreme. One is somehow the tightest one, and the other one is the longest one that you can have. And you want to know, well, what is the relation between the two of them? So let's say P is larger than 3, P is at least 3. The first condition, so maybe observation, is that N has to be less than something. So N is the genus of this knot. N. And the genus of this knot is P minus 1 P divided by 2. So by the proposition, N has to be at most P minus 1 divided by 2. There are no restrictions from the multiplicity because this has multiplicity 2, which is smaller than the multiplicity here. So, proposition. So let's look at the maximal N that we can find. If there's a deformation to Tn, T2 n plus 1 for some n, there's also deformation for every smaller n. I can compose deformations, and the proposition up there combined with his question. God, I forgot your name. What's your name? Sam. Combined with Sam's question tells you that, well, this deforms to T2 2n plus 1 for any smaller m, and I can compose deformation. So the only thing that I care about is what is the maximal n that I can find. So if n bar is the maximal such n, then, oh, now I need my notes. N is roughly between 1/4 and 3/8 of p squared. Which, if you think about it, is kind of crazy, because that proposition there tells you, look, you have to make either P or Q smaller, strictly smaller, and the other one has to be. So they both have to be smaller or equal to P and Q, but here we're actually growing quadratically with respect to Q. And if you try to think about how to write down an equation for such an object, you're like, how the hell do I do it? It's really not easy. And for the record, I think that algebraic geometers, so the bound that this construction is algebrogeometric, exhibiting the one large n is something algebrogeometric, but this obstruction is combinatorial, is topological. So this is AG, and this is top. And you would think that algebraic geometers know a lot of stuff. They have lots of tools, they have a lot more rigidity, and you would think that they can do something much, much, much better than this. Turns out that they can't, and that us topologists can do basically as well as they do on this problem and on many other problems that are related to this. Jeff is perplexed.
I guess I'm wondering, like, how sharp is this? I mean, are there examples where you can get sort of arbitrarily far to the left, close to the left?
No. We're very close to. I mean, this is constructing an example, right? Finding lower bound for the maximum means constructing examples. And we're constructing examples that are really on this side of the story. I think we're pretty far from filling the gap, and we need new ideas. And I think it's believed that we should be really on this side.
I guess maybe the other thing I was trying to ask, do you sort of expect that n bar should be some sort of function of p?
I mean, it is a function of p. You want, is it a polynomial function of p? I don't know, maybe?
Yeah, that's right. Yeah, that's what I'm wondering. Is it, do you expect that it to be just like a quadratic?
No, just because it's asymptotically, yes, but I don't expect to have exact values at every point. Right. What do you want me to do first? The construction or the obstruction? Jeff? Construction. Good. So what is T2 to n plus 1? Or rather, what is T2 to n plus 2? It's a link to begin with, so I'm already cheating. But this is the link of the singularity x squared plus y to the 2n plus 2 equal to 0. And this is a difference of squares. So this locally factors as x minus I y to the n plus 1, x minus I plus I y to the n plus 1. And the zero set of this is just the union of the two zero sets of these two. So this is a singularity that corresponds to having two curves that have a very high order tangency. So these are two curves that are non-singular. Each of them is a graph. It's of the form x equals something, so it's a graph. Well, turned the other way, but still a graph. This is another graph, so they're both non-singular, and they have a high order tangencies because you just solve the equation and you realize that 0 is a common root of multiplicity n plus 1. So the picture that I have in mind is you have this and you have this, and they, yes, or that. Great. Thank you, Jeff. Right, so whenever, and actually it turns out that whenever I see two curves that have such a high order tangency, the link that I see of their singularity is exactly the T2 to n plus 2. So what do I want to do? I want to create a deformation of something that looks like this. It looks like two curves that have a high order tangency, to something that looks like x to the p. So I want to create a deformation of something that looks x to the p plus y to the p, equals 0, to something that looks like this. Let's write down something, otherwise I'm making no sense. So this is just to tell you how I got to finding the example. So let's consider this deformation, T y minus x to the, and actually let me suppose that p is even. Just for convenience. Minus y to the q times t y minus x to the q plus y to the q. This is my f t.
So they're all Q's, right?
Those are all q's. Yes, q, 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 q. So when t is equal to 0, I'm just erasing everything. This is x to the p minus y to the p.
So wait a minute, they're all Q's or they're not all Q's?
These are x's, these are y's, and these are q's.
What do they?
Q is
Oh, P is Q. Ah, okay.
so when t equals 0, I see xp minus yp, which is not really t, the thing whose link is tp p plus 1, but we're almost there. This is similar to yp, xp plus yp plus 1 equals 0. And similar is what explains this O of p. And when t is non-zero, well, now this curve becomes a graph. This curve becomes a graph. And you can verify, it's not quite the same situation as this, but you can verify that these two curves are both graphs, they're both smooth, and that they have intersection tangency, order of tangency, which is q squared, give or take. So you have two curves that have order of tangency equal to q squared, which is p squared divided by 4. This is really just literally solving the equation. So what did I obtain? I obtained a deformation from the singularity, whose link is t2 2p squared divided by 4, from the singularity at t equals 0, which is t p p. And now I can compose deformations. So I have a deformation from t p p plus 1 to t p p, which is basically the one that's up there. And then from here I have 1 to 2 t2 2p squared over 4 minus 1. And this corresponds to having n equal to p squared over 4 minus 1. So I haven't talked about links and algebraic links, so I can't quite tell you explicitly why this cobordism is very small and why this cobordism just gives you an O of p here. And I can't quite tell you why this cobordism gives you an O of 1, but maybe I will say something at the end, maybe. And so this accounts for this lower bound. So for the upper bound, I wonder what I'm going to use to say something about this. We have signatures. Let's play with signatures. So how can we compute the signature of t p p plus 1? We know how to compute it, but somehow I want to see what happens in the limit. Doing exact computations with these things is very hard. So let's try and do approximate computations instead. So remember that we have this p by p plus 1 box in which we have all our points. And for a given alpha, I was drawing these two lines, and I was counting points in between and counting points outside. So this is x over p plus y over q equal alpha. This is x over p plus y over q equal alpha plus 1, and I was counting points in between. But if p is very large, the number of points that I have in between is roughly the area of the region in between, well, scaled by p. And the number of points that I have outside here is roughly the area scaled by p. So for the colorblind people in the audience, this is the red part. No, actually, this is the red part, this is the blue part. I'm counting points in the red and subtracting points in the blue. So the number of red points is roughly the areas of these two triangles. So this is T1 and this is T2. And the number of blue points multiplied by p squared. And the number of blue points is roughly p squared times the area of the rest. So you just need to know where the lines intercept here and here and here and here. And of course, q here is p plus 1, because I forgot. And this is just a silly computation. You just compute areas. And it turns out, I'm not going to do the computation exactly, but this function at e to the 2 pi I alpha is approximately, now I need to find it, 2p squared alpha, alpha minus 1 for alpha less than half. Actually, it doesn't matter. For alpha in 0, 1, though, this does matter. And it's just a matter of counting areas, measuring areas. And the other thing that we want to compute is what happens for the torus knot T2 to n plus 1. But then the picture is much, much simpler. You know, I have this rectangle with just one dot at a time, and this is what Livio was saying, that you can compute the signatures, and you can show that the signature is decreasing up until the half point, and then it decreasing, and then it goes back up again monotonically. And this behavior is essentially linear. So what you can prove is that the signature of T2 to n plus 1 of e to the 2 pi I alpha, this is roughly minus 4n alpha if alpha is less than 1/2. And then on the other side, it just goes back up symmetrically. And so what you're going to see is that you have one signature function, which is a parabola, and another signature function, which just dips down. And you want to compute the distances between these two graphs. Why? Because the distance, so the maximal difference of signature in absolute value gives you a lower bound for the cobordism distance between K0 and K1. And we know that if a cobordism, if a deformation between the two exists, the cobordism has to have genus, which is something that we know explicitly. So we expect, and we want, that there exists a cobordism with genus equal to genus of K0 minus genus of K1, which is something that you can compute explicitly in terms of p and n. This is p minus 1 over 2 minus. Good. You can have some fun, or yeah, maybe not so much fun, but you can sit down and compute, and it turns out, so what is not interesting? What is not interesting, let me draw them on the same picture.
So what is delta sigma just for slow?
The difference of the signatures.
The maximum over alpha.
Yes. So I'm going to draw the same picture that I have here. And this example that I've given already, so when n is equal to p squared over 4, the tip of this is already hitting, is already going below. Or if it's not below, it's really just at the boundary. So it's not interesting to compute the difference for small n, because already we know that for some large n it's realized. And the larger the n, the pointier my signature function will be. So what I need to find is whenever the tip of the signature function goes lower than the tip of the parabola, I want to compute the distance between the two graphs, the vertical distance between the two graphs. And it turns out that in this case, independently of p and of n, the maximal distance is actually in the middle. So a bit disappointingly perhaps, but the Murasugi, the classical signature, would have already suffices for this, but a priori we could not know it. And it turns out that the maximal distance between these two graphs is what? I computed it. I'll spare you the computations because they're not particularly interesting and because I will get stuck. I did not write it down because I'm not very smart. But the difference between the signatures is, well, I can compute it there. So this is p squared over 2 minus n minus 2n. So 2n minus p over minus p squared over 2, because we're supposing that the tip goes down. So n is larger than p squared over 4. And we want to show, well, we want to understand for which n's this quantity is larger than this quantity. If the maximal difference is larger than the genus we expect, it means that the cobordism that we want cannot exist. So we want that 2n minus p squared over 2 is smaller than, well, something that looks like p squared over 2 minus n, which hopefully tells you that n should be what I claim to be. 3p squared. Did I screw something up? Yes, I did screw something up. So I've done these computations maybe 4 times, and I've got like 4 different results. So I don't expect to get the results right at the board right now. But if you combine the 2 computations, oh, there's a 2g. There's a 2g here. So this should be a 2. This should be a 2. And then you do get exactly what I want to get. Yes. So this implies that n is at most 3/8 p squares. And now you might complain, first of all, that I'm going over time, but also that, well, you've been telling us the whole story about, you know, you play with these signatures, you do these complicated things with Hermitian forms, and then the examples that you give us just works with the ordinary signature. Yeah, you're a bit of a jerk. Yes, I wanted to be less of a jerk, and I wanted to give you one example in which you actually had to look at more signatures than just the Murasugi signature to prove that there is no deformation. And so I think that Livio will stay here on Friday afternoon after lunch to tell you how to do the next example. Do you agree with that, Livio? Great, thank you. So example, there is no deformation from T2, T316 to T229, even though all restrictions are satisfied. The genus of this guy is 16. The genus of this guy is 15. No, this is 15, and this is 6, and this is. Did I what? Oh yeah, so 15, 14. Good, thank you. 15, 14. So we expect to look. We want to look for a genus 1 cobordism between the two. If it came from a deformation, this would be the case. The multiplicity here is smaller than the multiplicity here, so no obstruction there. And this Murasugi signature differs by 2 for the two of them. But there is a value at alpha around 0.292. If you want to check, there is a value for which the difference of the signatures is actually 4 and not 2. And then I want to say much more, but I think I'll stop here.